Yeah, okay. Yes, thank you for the opportunity to speak. And thank you indeed for organizing the conference. And yeah, thank you to Hubert for, well, for inspiration, as it says here, but also for being a friend. Okay, and I think this talk is my role is usually to be the weird guy in the room, and in this meeting I think I could do that. So this talk will be a bit of an outlier, but hopefully entertaining to Hubert, at least. So, as is often the way with seminar talks, my main aim is to explain the title, spin chain braid representations. So, a braid representation is, in one of the contemporary languages at least, a monoidal functor from the braid category B. In a minute I will confirm to you what the braid category B is. It's going to be what you think, but I will do that in a suitable idiom. A rank n charge conserving representation or spin chain representation is a monoidal functor from some monoidal categories, such as B, to the category match n of rank n charge conserving matrices. And again, I will tell you what that category is in a minute. And then, so having explained those two components of the title, in the work itself, we construct all spin chain representations up to isomorphism. I should drop back and say this is joint work with Eric Rowell, Texas A&M. Okay, so classification of braid representations is a major open problem, or at least it would be, except that it's impossibly wild, so nobody is going there. On the other hand, for applications, conceding that impossibility is not really acceptable. So here we seek a framework for paradigm change to get past that impossibility. Eric Rowell has his own set of clues prompting the way we've gone at this. It's probably useful for me to say that my clues come in part from recent developments in higher representation theory, the work of, for example, Mazurchuk and many others. This is around two vector space categories, that kind of thing, Kapronov, Voivodsky. And another major suite of clues comes from higher lattice gauge theory, work of Mario Martins, and again, many others. Okay, so we're going to address the problem with a paradigm change. So when we've solved it at the end, there'll be a question of how universal is the construction? How good a job did we do of making the impossible possible? And I'll come back to that at the end. Right, okay, so the first thing I said I was going to do was get you and I in the same idiom with regard to braids and the braid category. So, well, the braid group itself has occurred already many times in this meeting. So I think everybody knows what it is. The idiom that I'm going to use is kind of the defining one. So the group acting on either of the spaces that you can see indicated in those pictures there, it acts in the way indicated by that picture at the top there. And then in this idiom, the bottom left would be the identity braid, and the right would be something a long way away from the identity braid. So I trust no surprises there. The take home from these pictures is the idiom that I'm using, and the next bit then should just work. So this is the category, the monoidal category indeed. The monoidal composition is in the idiom that I've introduced exactly as indicated by these pictures here. Okay, so that's convenient take on the category B. So if you're with me, you will see that that category is monoidally generated by the elementary braid. Let me just have a go. Annotating the schematic of the elementary braid. Is that coming out? Yes, it is. So that's the elementary braid, which I'm going to call sigma. So that lives in B22 because there are 2 strands to 2 strands. And monoidally generated. So the point I'm making there is that, of course, I could tensor that guy with that guy, and I would then get this guy. Right, so we do have enough hardware here to explore the operative features of the braid category. So we only need the sigma, the elementary braid. So a functor f, monoidal functor from B to some target category, some target monoidal category, is determined simply by the image f sigma. That's all we need. So the next question is, what is this match n that I referred to? So let's do it like this. Fix a commutative ring K. Of course, I'm going to say K equals C for you guys. Mat, then, is the monoidal category of matrices, the usual category of matrices, and I'm going to use the AB convention Kronecker product. It doesn't really matter which Kronecker product convention I use, but it's handy to note that there are 2 standard conventions for the Kronecker product in popular use, and therefore there's a Z2 action flipping between those conventions. The conventions aren't important, but that Z2 action, which is a monoidal functor between the categories built by the 2 conventions, is a symmetry of our solution space, so I can use that. In the same spirit, so mat is the category of matrices, so the objects of this category are the natural numbers telling us how many rows and columns our matrices have. So I'm going to label the rows of object n. So object n, that means there will be n rows. I'm going to label those rows by the symbols 1 up to n. Surprise, surprise. So that's a triviality. Again, that's just a convention. It's a slightly loaded convention, though, so everybody has a natural order associated to that particular symbol set. That order is arbitrary, along with the choice of the symbol. So that just means that there is also a symmetric group, sigma n, action, and there's a functor associated to that, which will act on space of solutions. So that will be handy. Okay, mat n, for n a natural number, is the monoidal subcategory generated by object n. So just like before with the braid category, we had a horizontal composition to make the wider braids by horizontally combining braid group elements. So I have this monoidal composition, which is Kronecker product here, and I could start with any object and see what category is generated by that object. And if you're with me, you can see that the subcategory generated by a particular object n will just be all the matrices whose row and column sizes are powers of that capital N. This is very much not rocket science, just organization. I'm going to rename that generating object n as 1 in mat n, and then the monoidal composition on objects becomes addition, just because it's the power, right? N to the power of m, and the object composition in the original mat was multiplication, but in this category it's natural to think of it as addition, which fits well with the Braid category, which also has object class for natural numbers, and their monoidal composition is addition. So 2 strands of hair together, 1 plus 1 gives 2. Okay. Consider a matrix in this mat n, and in particular in the morphism set mat n, mn. So that's m by n, n to the m by n to the m matrices. I can index the rows and columns of these possibly bigger matrices in what I hope is an obvious way by taking words of length m and n respectively in my symbol set 1 up to n. So yeah, the set of all the words of that length clearly has the right dimension to label the rows and columns of such a matrix. So with that kind of minor bracket notation, then I can give this notion of charge conserving. So a matrix in mat n mm is charge conserving if the WV matrix entry non-zero implies that W is a permutation of V. So that's the word W is a permutation of V. So everybody here, so we already this morning we have many matrices of this form. I'm just speaking out the organizational scheme because it'll be useful. Right, and in particular those matrices form a subcategory of mat n, which I'm going to call match n. So that's charge conserving rank n matrices. Oops, need to go there. Right, so yeah, let's visit this R matrix page again. We said that there's a generating braid sigma, and therefore I can tell you a representation by telling you the image F sigma of that elementary braid, and now we can see that that should be in match N22. So its image will be a sparse matrix whose rows and columns may be indexed by ordered pairs ij, with the I and j taken from 1 up to n, and the charge conserving condition says that the non-zero blocks are the sort of II block, which is 1 by 1 if you like, and the IJJI block, which is 2 by 2. I'm laboring this point at great detail because it's going to be useful for me to work with these things, to put those in the trivial natural correspondence with the vertices and edges of the rank n complete graph. Right, the rank n complete graph, it's got n vertices and it's got an edge for every ij pair. So there's nothing to that, it's just that I can think of my candidates for representations as decorations of the complete graph. Okay, so just in case you've forgotten, yeah, so I'm looking at your, there we go. So here are indeed my rather poor sketches of the complete graph K2, K3, K4, K5, and then K10. Finding something that isn't horrendously large but has enough rank to be generic for this story is a bit of a struggle, but I think K10 will do me. And okay, I am going to need to orient, but I don't want to labor the orientation on my complete graph. So think of it this way. We're going to draw on the plane, of course. do a clockwise numbering to total order the vertices of the complete graph, and then just orient so that we have an edge ij, directed I to j, whenever I is less than j. Oh yeah, okay, this figure already has a partition of the vertices, which you could ignore. Right, so what the point of that was that a configuration on the complete graph is going to be an assignment of a variable to each vertex. So A2 there, I've already drawn A4, and a 2 by 2 matrix of variables to each directed edge, and I've already drawn the 2, 4 incarnation of that there. So the snippet of my solution to the Braid representation challenge localized at 2, 4 would be something like this. So that'd be A2 there, A4 there, and then this guy going here. So I'm trying to introduce a language where solutions look like configurations of this form. That will help me. Okay, so before I state the theorem, the classification theorem, let's have a quick warm-up about how to read it. An example of a classification theorem, one that you all know very well, is of course Young's classification of the irreducible representations of the symmetric group over the complex field. Here one says that irreducibles can be classified up to isomorphism by the set of integer partitions. And this is a win for us insofar as that set is relatively well understood. Here, analogously, we'll need to introduce notation for some further relatively straightforward, not so straightforward, but relatively straightforward combinatorial structures. That will give the index theorem, and I'll also give a construction for the representations and introduce notation for that too. Right, so I'm talking about giving you a sequence of decorations of the complete graph which correspond to representations of the Braid category. And okay, this figure is kind of the heart of the story. This is the combinatoric that we need, at least in sketch form. So on the left there, we've got, should I wait? Yes, you're slightly behind me on the pages, but you're there now. On the left, that's K10, complete graph of order 10. And on the right, I've kind of Cézanne-ified, that's definitely not a word. I've used the artistic license of Cézanne to explode my complete graph into, it's still the complete graph, but I've indicated a partition of the K10 into in this example, a K5, a K4, and a K1, pulled apart with, the connecting edges still there. So I need first to partition the vertices, my complete graph, and then, well, I'm going to have to give you a set of 4 tuples. This is what the replacement of Young's classification for the irreducibles of the symmetric group looks like for this harder problem. Not just an integer partition, but a certain 4 tuple, and 4 tuple, that's a bit much just after lunch, but I try to lead you through it with this picture. So first of all, P here, partition the vertices into, well, any number of parts. So I've done a 5, 4, 1 partition there. Then the second component of my 4 tuple that I will need for this index scheme for representations is a refining partition to that one. And I've indicated that with this beautiful lilac color. So these lilac overbars are indicating the clusters of this second partitioning. So that's a partitioning that respects the big blue partitioning and refines the individual parts of that further. The third component of the combinatorial structure that I need is a total order on those parts. By the way, Eric and I call that initial partitioning a partitioning into nations, and the second partitioning a partitioning into counties, the English subdivision of nations. I'm not going to tell you what we call the total order on the counties. Suffice to say that Yorkshire is number one. You knew that already. And finally, we have a partition of the counties, but only into two parts. The previous partitions were into any number of parts. This is only into two parts. So this is possibly slightly bewildering combinatorial structure into four tuples. The rest of the talk is going to be showing you that this set indexes all spin chain Braid representations, and indeed exactly gives us a construction problem. Yeah, okay, I've kind of said what those things mean, so let's give the vernacular form of the theorem. For each natural number n, that set, Sn, of four tuples that we just wrote out, indexes a transversal of the set of charge-conserving Braid representations up to equivalence. That's all I'm going to say about the theorem for now. I'll conclude the construction once I have the machinery from the n = 2 and 3 cases. The outline proof is going to be, first we give another theorem formulating sufficient, necessary and sufficient conditions for a solution. This is kind of analytic heart of the proof of the main theorem. Then we solve those conditions in ranks 2 and 3. And then we'll need a couple of quick lemmas exploiting some magic in those solutions to solve the general n classification and construction problem. Okay, so before I give the analytical constraints, let me remind you one more time about how to read these things. The labels that I'm using for the entries in the F sigma, which gives the representation, are these. So AI on the vertices and these A, B, C, D 2 by 2 matrices associated to the edges. And armed with that, you can now take something home from this theorem. So this theorem says let F be a monoidal functor from the Braid category to mat n, that is indeed to match n, because it's the level n charge-conserving monoidal functor, thus determined, as we've already said, by F sigma. So the Braid relations, and hopefully you can see from my sketch that I did of some hair and some braiding earlier, that is the constant Yang-Baxter equation, or however you like to think about it. So that implies the following constraints on entries expressed in this ABCD form of F sigma. Sadly, we must also include the images of these constraints, which are their orbits under the action of this symmetric group cross-flip symmetry that we mentioned right at the beginning. So this is a rapidly increasing number of constraints, and sadly, you now see that we're confronted with a significant number of simultaneous nonlinear equations blowing up as n gets large. And this is the point where usually everybody goes home. Well, okay, Hubert didn't go home before doing the n = 2 case. So we could at least have a go at the n equals 2 case. But then after that, everybody goes home. So let's have a look at the n equals 2 case specifically in our charge-conserving form in a minute. And then we'll look at n equal 3. And then as I say, we'll prove the theorem. So, yeah, let me not dwell on the proof of that. It's a mixture of analytical and abstract nonsense. One thing, maybe I didn't let you look for very long at the constraint equations, but one thing that we could do, looking briefly at the constraint equations, is to note that this combination always comes together. So if you remember, these are the off-diagonal terms in the 2 by 2 matrices. So you're probably not surprised then to see, it's actually not completely obvious, but hopefully not surprised to see that because of that symmetry, we can, if we want, render the 2 by 2 matrices into some canonical form of choice, this lower 1 form, or maybe a symmetric form as well. Okay, so here is the result for n equal 2. I'm going to show you a schematic form of this, which will be much more useful. So the take-home from this page really only needs to be that hopefully you were expecting in rank 2, so that's 2 squared by 2 squared matrices. So hopefully you were expecting a sparse 4 by 4 matrix of that shape there. And so those are the labels, and then down here are the solutions. So these guys get constrained in various ways, and I want to skip over this formulation and just give it to you in summary. So, okay, here's the summary sketched out. The way to look at this is, right, we're in n equal 2, and that means the complete graph that we're decorating is just 2 vertices, 1 edge. So that's what you're seeing here. You're seeing 4 different schematics for solutions consisting of 2 vertices, 1 edge. And so the point, of course, is that from that data, we can build this thing which has something here, 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 and here. And we take that guy and put it there. We take that guy and put it there. And we take the matrix and put it in the middle. At rank 2, this looks like a rather laborious way of writing out a nice innocent 4 by 4 matrix, but believe me, in higher ranks, this will be a lot more useful. Okay, so let's have a quick look at the summary of, so this is all spin chain solutions up to equivalence in rank 2. What you're hopefully expecting to see, at least, is this first one. So this first one is a scalar multiple of the 4 by 4 unit matrix. So scalar multiple, because of course this is representations of the Braid group, so we're always at liberty to rescale by an overall factor. So that gets called the trivial representation. Trivial is too long to write for my purposes as a configuration label. I'm just going to call it 0. The next one is somewhat different. So now we have different variables at the vertices, and we have skew diagonal, and different again variable on the 2 by 2 part. That's sometimes called classical. The symbol I'm going to use for that is slash. This one occurs all over the place in the literature. You probably used it yourself. The next one also very common, or at least in the orbit. I've written it in a slightly strange form, but in the orbit. So this one has now a less sparse decorating 2 by 2 matrix. The variables at the end must be the same. And I call this one F, and that's short for ferromagnetic, just to remind me that the variables at the end must be the same. This one, in its orbit, there is the famous classic UQSL2 braid representation. Okay, A then, the last one here, that's antiferromagnetic, and that's just because the variables are not the same on the vertices, otherwise it's somewhat similar. And in this orbit, we have the slightly less famous, but still well known to Hubert, UQSL1 bar 1 representation. So, nothing new there. But it's a useful warm-up exercise to get you used to these pictures. I'm going to skip over the proof. So, armed with those pictures, if I tell you that now I'm going to give you the solution at n equal 3, you should be expecting decorated triangles. And that's what I'm giving you, decorated triangles. So here we are, these 9. These, so it was 4 before, now it's 9. These are the various distinct varieties of solutions in rank 3. How do you unpick this? Well, you can see that, well, hopefully you're expecting triangles, and so this tells you how to populate the entries of a sparse 9 by 9 matrix, which is going to give you your braid representation. So yeah, lurking in here somewhere is the classic UQSL3 representation, which has already appeared in a couple of talks. In fact, it's lurking specifically down here, but that's a bit hard to tell in this notation. So yes, I am giving you these 9 by 9 matrices, don't forget, by giving you the various 2 by 2 blocks. Well, depending on how quick your eye is, those 9 are either a sort of a bewildering, off-putting, or possibly beautiful collection
Paul?
of. Yes.
So sorry. So can you wrap up in like 4 minutes?
Yes, I can.
Thanks.
Yes. Yes. Thank you. Yes. So right. But let's skate over the proof of that. You can see various miracles occur. So how are we going to prove the general case? We need an assignment of a scalar to each vertex of the complete graph Kn, and a matrix to each edge of the 6 types. So that's the slash, the 0, the f, and then the f underline and the a underline. That would be the f and the a, but on the oriented edge with the opposite orientation. And then an admissible configuration is going to be a configuration such that every triangle configuration is one of those 9 forms given above. This is another one of those points where you're confronted with K10 and those 9 constraint rules, Plaquette constraint rules, and maybe you feel like going home at that point. But actually, with this 4-fold partitioning organizational principle, we can construct all of the solutions that, that there are. So, okay, in 2 of the 4 minutes available to me, a key lemma is this one, an edge to coloring, so that's a coloring not of the vertices but of the edges of the complete graph Kn with a color set, and choose any symbols you like. I've chosen X and Y because I want to use them sometimes for my slashes and sometimes my 0 labels. It's called parted if every triangle that has 2 Ys has 3. So in other words, there's no triangle that has exactly 2 Ys. The reason that I'm quoting this lemma at you is because it means that the set of parted colorings is in bijection with the set of partitions of the vertices. So if our Plaquette conditions have this property on triangles, we can tell that solutions can be given by constructing partitions. And I guess this is probably the last time we're going to go back here. But you can see that well, if you're quick, or you can just trust me, that the complement of the slash conditions on these triangles obeys that parted rule. So the slash conditions will give a partition of the vertices of my complete graph. So that's why we have this Cézanne partition here. And let me, okay. Right, 1 minute. So let me show you. The slash data is going to induce a partition in the way that I've indicated there. The zero data is going to introduce this county partition. Go back and look at your leisure later at the triangles to convince yourself that is true. And the AAF data is going to introduce the two-part one. So in my last minute, let me summarize. So already in this picture, if I want to construct a representation from this picture, I've already done the slash level partition. So that means that I should decorate all these guys with a slash, and the lemma also said that we should associate the same variable to all of those. 1, 3, and these will all be decorated with a slash 2, 3, and then these all with a slash new, I guess, 1, 3. We have the county partitions, maybe something like this. And the total order, if you like. And then, oh, I need another color. The two-part partitions. And okay, so I am going to associate the vertex variables alpha 1 to everything in this part, and then beta 1 to everything in this part. And if I have an edge between two parts, it's an A, and within a part it's F, and within the county parts it is 0, and I should stop there. So that hieroglyphic there is the construction method for all solutions. Okay, so congratulations, Hubert.
All right, so thank you very much. So who is that? Sorry? So can you tell us who this is?
I think it's Cézanne's wife.
Okay. Well, so the previous concluding slide was not bad either. So are there questions? Hubert?
Hi, Paul. I have a question. So basically, if I understood correctly, you're doing like classification of matrix solution of Young-Baxter equation without spectral parameter.
That's right.
Can you do similar classification for Young-Baxter with a spectral parameter?
Right now, no. But of course, that's one of the next steps. It wasn't literally next in line. Next in line was Tangle. Yeah, so the short answer is no, but so as far as I can see, it's a miracle that this works. As I said at the beginning, this is not supposed to work. And
yeah.
So that makes one optimistic, so it would be worth a try. But yeah, with every miracle comes a very steep curve, right, if you try and generalize. So we'll see.
Or can you Baxterize your solutions? I mean, some of them are Baxterizable, we know. Can you Baxterize your solutions?
Yeah, well, right. That's the right question. But my answer remains. I haven't thought about it yet. Yeah, I mean, so I was glib about the analytic work. So my collaborator, Eric Rao, is a genius at the calculations under the derivation of that proposition. So as it says here, so now you've asked me a question, there are finitely many cases to try, 6 to the 3, but those cases are analytically complex. Various miracles happen so that you can derive these solutions. You're asking me on top of that miracle to deform away. So yeah, maybe there's already been one miracle, but yeah, no idea.
Oh, thank you. It's impressive work. Thank you.
Hi, Paul. So we're used to thinking that representations of the Braid group have to do with monodromy and conformal field theory. Any idea what, so for instance, you know, the Jones polynomial is related with Vesuminos on SU2 and so on. Any idea what kind of conformal field theory might be lurking behind your solutions?
No, that's kind of why I'm showing it to you. So yeah, in 30 odd minutes, that was probably a bit of a difficult ride, but anyway, maybe your curiosity is piqued. But yeah, this is the right question. So my very pathetic answer to that is in terms you know. So already if we look at this one, so I think you understand everything on this page very well, but I can still point at it. So interesting things are already starting to happen here. And when we generalize in this way, it gets a lot wilder. So yeah, I don't know, but it's exciting to think about.
All right, so thank you again. Thank you very much.